Welcome back, everyone. This episode, let's take a look at the relationship between position and time, which means we're observing motion. We're observing some motion happening. And we typically are, when we think of this concept, we just want to think about a horizontal plane. The vertical position will be something that we save for later because there's some other variables that we add into that, obviously gravity. And gravity is a factor here, but in these early concepts, what we do in physics is we eliminate all of the other factors that can and do play a role in the motion, and we basically distill it down. We sort of simplify it down to the basic concepts that we can observe directly. You can observe directly an object's position, and then you can directly measure, so you can observe some amount of time that has elapsed. So with that said, let's jump in and take a look at position time graphs and how we go about putting them together. Take a look. Let's take a look at position time graphs. Probably one of the most fundamental parts for the physics class that and the concepts that we're going to be looking at. So we've got two objects here, object A, object B. We could call them whatever we want. So the two objects, it tells you we're moving with constant velocities. Object A is moving at a faster rate than object B. Make a graph that represents these objects' velocity, and then we're going to write an equation. So it says graph, so let's insert a graph. So how about we get just some sort of basic graph going here, right? So we've got this basic x and y, right? So we've got our x and we got our y. So let's go ahead. We know that over here is our x. We know right here is our y, correct? And then we've got some motion. So there's a couple ways of thinking about this, right? So we know, what? I really like those. I like those straight lines. Let's use that. All right. So let's just think about it. We could have a situation like this, and I'm just going to bisect this at what looks like a 45-degree angle. I could put it at any angle, it doesn't matter. But let's think about what this means here. So we're not worried about object A or object B yet. We're just kind of talking about just this concept with this graph real quick. So if this is x, this is y, we know that a line like this on a curve, this would represent something with a constant velocity, because we would infer that this slope line, okay, so this is a slope line, m, slope, right? So we can assume that this slope line would represent the velocity, all right? So would represent velocity. I know it looks like a check mark, but that's a v, all right? Represent the velocity. And then what we want to think about is if we're looking at a concept like this, then obviously, this is time, and typically seconds is how we measure that. And then right here we would have position, right? Position, which typically we think of as a change in x or a change in y. So we're just kind of doing some linear motion along a horizontal. Think of that like something moving, all right? And of course, that would be measured in meters, okay? When we get to stuff with vertical displacement, then we would call that delta y, right? I mean, that's in a previous video in a lesson we've talked about that. Okay, so right here, we can, where this point is right here, where this intersects right here, we know that to be what? Well, if we go back to this concept here, y equals mx plus b, then this is your y-intercept right here. All right. Now, there's a couple of things that could happen. We could have right here, it could very well be that you start from, say, rest. All right. So where b equals 0, if b equals 0, then if you think about it, b equals 0, then now you just have y equals mx. So now we think about this, y is our position. All right, y is our position, which is delta x. M is our slope, which is our velocity. And the x right here we know is time. That's our change in time. You should be able to see very quickly that if I were to divide both sides by delta t, that I wind up with velocity equals the change in position over the change in time, which this is essentially our basic equation for speed or velocity, right? So what if, so here's a situation. What if b is greater than 0, right? And so, and zero is relative. In physics, we're going to find 0 is a very, very, very relative concept based on many factors here. So let's get ourselves another graph. All right, let's insert another one of these things. I'm liking this. I love this tool. This is a great little tool here. All right, and let's go back to where we were right here. Let's insert another one of these. Well, what happens if, let's just say that thing had started right there, right? Well, this kind of represents, this looks like it represents the concept of b is greater than 0, right? Because we assume here is, so we assume x, here's our m, which is our slope, right? And then, of course, this is our y, and we know that, again, that this is position over here, this is time over here, right? And so, again, so position will stay with delta x, all right, measured in meters. And, of course, this is time. Of course, default for that is seconds, right? And so this thing is greater than 0. So we're still starting out with, all right, let's move this up a little bit. We're still starting out with y equals mx plus b. But now that it's greater than 0, all right, if we know that the y is basically your change in position, x, m is a slope, this x variable right here we know is the change in time, plus b, all right, so you start thinking, wait a minute, I've got to subtract b, right? I got to subtract b from this and move all that over there on that side, right? So I've got delta x minus b equals v divided by t. All right. So now let's divide this side by t, divide this side by t, and then we're going to basically get velocity equals delta x minus b over delta t. So now we have this right here. Okay. So let's think about this. B and x, what do they kind of refer to? Well, let's think about this for a second. Let's go back to this part. Let's go back to this part right here. All right. We've got delta x equals v delta t plus b. All right. So the delta x, that is this. That is the y variable, which is the position. So a change in position. So now let's think about this for a second. B being your y-intercept. I don't care if you're here or here. All right. B being your y-intercept. Let's think about this. If this is where the object started, it must be relative or in relationship to whatever this point is, or this point, or this point of position. So if we think about it, this probably equals the initial position, and this up here equals the final position. All right, so let's think about this for a second. Let's rearrange this now. We can write this delta x equals b plus v delta t. All I did was I just reversed the order of that, and it's still the same thing. It's still gonna be the same thing, right? Still gonna be the same thing. Well, now if we know that this right here, if we know that the b represents your initial, and this would have to represent the final, all right? So now, what would you do? You would subtract this from this side, so we get the final position minus the initial position equals v delta t. Now that should look familiar because in your slope intercept, right? When you've got this form right here, you're always looking at delta y over delta x. You're looking at the y being the change in position, the x right here. What we're looking at is like y2 minus y1. In this case, we're just using f, right? So this right here, this part right here, and I know this could get confusing because you see x here, but we know x is position. All right, it's the position of it. Sometimes the d can be used, right? But it typically not. All right. So now if you think about this, divide this side by delta t, goes away. Divide this side by delta t, so we get velocity equals delta f minus, I'm sorry, x of f minus xi, the final position minus the initial position divided by t. If we want to reduce that down, we know that this right here is really delta x over delta t. It's the same equation. It's the exact same equation. All these equations, when there's a linear relationship, come from this basic concept that we've learned in algebra. So we can apply this everywhere. I mean, even calculus uses this basic concept, but it goes further, and it looks at other parameters, other variables, in slightly different ways. But at the heart of it, it all comes down to, if the relationship is linear, then this relationship that we see in y equals mx plus b, it holds true. And so all we have to do is define our variables. We have to define m, we have to define x, we have to define y, we have to define the b. Once we've done that, it's just plug and chug, and we're done. All right? So let's take a look at that. Let's practice a problem. So to finish answering this particular scenario, let's get ourselves another graph. I like considering these graphs. These are fun. So, there it is, right there. Let's get ourselves one of these. Okay. If A is a certain distance directly in front of B, again, remember we said it's all relative. The two objects move with constant velocities. We represented that here and here, right, with that nice clean slope line, right? A is moving faster than B. Okay. A is moving faster than B. So let's it says, what again? A is moving faster, so that means it would be at a faster rate. So I'm just going to exaggerate and draw a really sharp or really steep slope. And then we can go ahead and assume that right here B has just less of a slope. All right. This is just your line. What you draw can be a lot longer than this, a lot shorter, probably not much shorter, but it basically could be something like that. There's nothing that says that B doesn't start down here at 0. B could be starting here. It's just that we know that it says A is a certain distance directly in front of B. So whatever you draw graphically just has to represent that concept, right? And so now that we have that, we know that right here, this has to be A, that has to be B. And of course you have X and Y, and put the titles of your variables as well. I have less room, so I'm not doing that, but we know it has to match what's up there. Then of course remember that we want to define our initial and our final, so we would mark our initial and our final positions, right? Our XF, XI, and of course we got our change in time. All that needs to be done appropriately. I just have less room here, which is why I'm not marking it, but you know to go ahead and mark that. All right? Fairly easy. It's pretty straightforward, right? Object A is 1.5 meters directly in front of object B. This thing down here says we're going to need to make a graph, and we're going to have to write an equation for what we see happening between A and B. So let's go back to our handy dandy graph making tool. I love this thing. This thing is great. All right, let's slide that over. Give me some room here. All right. It says we've got an A and a B. The two objects move with constant velocity, so the slope line is going to be it's going to be a nice even slope if it's a constant velocity. If it's not constant, we would kind of see it moving back and forth. Sometimes that curve would kind of go up and it might be wind down, whatever the case might be. Just like you've seen from things we do in lab, the lab data that I post, things that we've talked about in previous lessons and videos. All right, so keep in mind, as long as your data points are pretty accurate and have very close precision, they're not scattered everywhere. So that slope line, all the data points are basically along that slope line instead of scattered all around the slope line. Right? It took me years when I was younger to figure that out. It didn't make much sense. Probably because I just didn't listen in class, but it didn't make much sense. But it makes sense now. All right, I'm rambling. Back to the problem. Okay, so A is 1.5 meters directly in front of B. All right, so we know the y-axis. Oh wow, that was a pretty ugly looking y. Y-axis, right? And so we know the y-axis is position, which is a change in x measured in meters. We know that this is time. And this y-axis, I probably should have made it a little bit longer, but this is just for training purposes. We typically would want it to we would want the axes to be as balanced as they need to be. So just understand that. Okay, so all right, so it says the two objects move at constant velocities for 5 seconds. So what that says is, obviously I'm going to have 1, 2, 3, 4, 5. All right, and 1.0, 2.0, 3.0, 4.0, right? Those attention to details, okay? And then A is 1.5 meters directly in front of B. So wherever B is, it doesn't matter. Wherever it is. So we could actually start B here, or we could start it here, but wherever we start it, A would have to be 1.5 meters in front of that, which means the point for A has to be higher. So let's just make it easy on ourselves. All right, let's make it easy on ourselves. If we call this 1 and we call this 2, then we're saying this is 0, and we're saying that 1.5 is right here. So if that's the case, then what that means is that we have at 1.5, and you see how we see where 5 seconds is. I'm going to come straight up from that to make sure that we end right there at 5 seconds. And then I'm going to do the same thing again, right? But I'm going to start here, and I'm going to stop at 5 seconds. All right, if we go up, I stopped at 5 seconds. All right, so this has to be 1.5 meters right here. This has to be 0 meters to hold to what this is saying right here, right? What the problem is saying, what the situation is saying that we have, right? So we know that this would have to be A, and this would have to be B. Object B moves at a slower rate. So with that said, let's think about it. The way that I drew both of these slopes, right? then they're actually kind of at the same rate. So let me click on this. They're about the same, right? They look like they both have the same sort of angled slope, right? So if it's moving at a slower rate, I'm gonna bring that down. You can see that angle right there. You can see this looks at a slower rate. It's not sloping quite as much. This is just we don't have the exact numbers, but conceptually, what we're doing is trying to get this to actually match up, right? All right, so let's go back to our draw feature, and let me put B right here. Okay, so now let's think about the equations for just a second. Let's go back to what we've done up here. All right, let's go back to what we've done up here as far as our relationships go, and we can use this to help us out with the way that we've drawn this here. Okay, so pause the video and then come up with your equations for what is here, and let's see what you've got. So for A, right, so the velocity at A, let's think about this. The velocity at A, we know that this is the initial, right? And we know that this is the final. That was a really ugly X. I'm going to go back and redo that for you. I want this to look good for you. So there is the initial. That's a little bit better. And then there's our final. All right. Oh, now the F looks bad. Looks better now. So there's our final. Well, if we know that velocity is delta x over delta t, then we know that this is the final minus the initial over the change in time. We're not quite sure because we don't have the rest of this here. Now we could figure this out if we had some other data, we could figure this out. But this is just a mostly conceptual question. We know the initial position was at 1.5 meters. And so we know for the velocity at A, we have the final minus 1.5 meters over that change in time, right? Over that change in time. Think about this for a second. If we go further, we know our change in time is basically t2 minus t1. In this case, t1, you start at the initial time. In this case, it just happens to be as soon as we started, we're at the 0 point, so to speak, right? So we've got x of f minus 1.5 meters over 5 seconds. So there's our equation right there for the velocity at A. Okay? There's the answer to our question on that. Now right here, and this is all true because right here B is greater than 0. Here, the intercept B equals 0. That's what we're calling it, right? So in this case, we've got the velocity for B equals delta x over delta t equals x final minus x initial over the change in time. All right, so if we know that this is our initial and this is our final, then we know that B, right, equals our initial. So right here, we know the condition is x initial equals B, which is greater than 0. All right, therefore, those 3 dots kind of mean therefore, right? Therefore, we know that this is true. That is equal to 0. So now what we have is the final over the change in time. This equals the velocity of B because we're dealing with a constant velocity. That's not too bad. I think we can do this. It's all about the conditions. Much of physics is the plug and chug part is not what's really difficult. What is the challenge is defining the condition according to what we see in the situation. Okay, that's the first thing you want to do. After you define your condition, then it's just a matter of labeling everything correctly, and the condition being what's the relationship of the curve or curves graphically or in equation form. What is the relationship that you're able to observe, and then just marking that out. The arrow that you see right there on the screen, where we put an arrow through, put a zero, that is a standard notation in physics, so that so that we don't have to deal with the trivial nature of just subtracting zero from something or adding zero to something. If we know that the value is zero, then we just take it out. The equations in physics can get massive. They can just get to the point where you've got so many letters and subscripts for subscripts separated with commas, and it can get extremely laborious to write out and very tedious in detail. So one good thing in physics is we want to eliminate what we don't need very early on. And so much of what is needed for this type of class is this type of sort of pre-thinking. I don't know, I'm coining that phrase. So if ever it becomes famous, you've heard it now, and it's copyrighted right now. I'll get the credit. You do some pre-thinking. Do some pre-thinking so that you can then, in anything that happens that changes in the situation, you already know the definition because the equation is the definition. Both of these equations that you see on the screen, those are what are defining the motion in this condition that we see here between the two objects in comparison. Okay? Hope that helped. I will see you again soon. Stay curious. Bye. And there you have it. Position time. So very simple. Y equals mx plus b. So we've got those variables that are in there. You've been working with those for a while. And to some degree, they will always be a part of what we're doing. Okay? Just keep that in mind. Position changes, and where you start is you or the object where it starts. It's all relative in relationship to another object or some prior motion or a lack of motion. That's what you have to keep in mind every single time. And a graphical representation and analysis needs to be reflective of that. It needs to sort of really exhibit the motion that has happened and is happening up until the time that, well, time is no longer being measured. I hope this helped. Pause, rewind, look at this multiple times, however you need. Definitely practice those problems that I provide for you. Answer keys are always there for you. And as always, I'm here for you. Stay curious. Good talking with you, and I'll see you soon. Bye.